Hello everyone. Today we have a new Kent lecture. We have Dr. Bhasin. Dr. Bhasin is a professor and Temple Foundation Endowed Fellow in the Department of Civil Architecture, and Environmental Engineering at the University of Texas at Austin. He is also the director of the Center of Transportation Research, which is a multi and interdisciplinary center that conducts research on all aspects of transportation. He is an active research. He has an active research program in the area of pavement and materials supported by a range of private and public agencies. His research and teaching have been recognized through several prestigious awards and honors, including the National Science Foundation Career Award, the CUTC Award for Outstanding Contribution to Research and Teaching, the University of Texas System Outstanding Research Teaching Award, and the American Society for Civil Engineers Walter Hoover Research Prize. We're so happy to have you here. Actually, at the beginning, when we were trying to come up with names, I met with Professor Alcaldi, with Javier, and Professor Alcaldi said, we're just getting the best people. And I think your name came on top of the list. So we're looking forward to your presentation today. Professor Alcaldi, I think you want to mention something before we start or after.
Oh no, I'm just very glad that you are here with us. I think I would say that Amity is definitely one of the top pavements people that we have. I used to say that he's a rising star, but he's already a star, so so he has more gray hair than I am. So he's definitely up there. We're very, very pleased to have you here. This is organized and coordinated by our students. So I would love to introduce you myself, but I think we keep it as our student activity, so welcome.
Thank you very much. Should I get started?
Yeah, yes, sir.
So thank you very much, Professor Alcaldi. And all the students have been getting emails about the organization and so forth. So I think the students have done a great job in organizing all of this. I don't know. I need to change that from wherever you downloaded that introduction to something smaller and shorter. Certainly, it's a great honor to be here. And as I was thinking about what did we talk about in terms of pavement research projects and so forth, I thought maybe what I'll do is I'll just go over snippets of different ideas that we've developed over the past few years. And since most of this is focused at graduate students, a lot of this is ideas that are a little bit out of the box or a little bit more looking beyond the conventional practice. But I must also mention that most of our sponsors, our research sponsors, tend to be DOTs and industries that are looking for really practical tools. So what you're going to see in your slides here is stuff that was not necessarily the focus of a particular research, but it was done on the sidelines of several different research projects. There's one research project looking at designing of ultra-thin asphalt mixes, and we've done a lot of work on the sidelines as we were working on that project. There's one project looking at recycle binder ratio or use of reclaimed asphalt pavement. We talked about that this morning. We did a lot of work on the sidelines of that project. We had in an SF project, a US DOT project that gave us a little bit more flexibility to try different things. That was good. So what I'm about to show is snippets of ideas of where we were and where we probably could be headed to. So this is about flexible pavements. I mean, we're talking about flexible pavements, specifically the asphalt mixture. Within the asphalt mixture, you have mixture design where you have aggregates and you have the bitumen. So what I'm going to talk about, focus today is mostly on this part, bitumen or the asphalt binder, the glue that keeps the road together, and focus on that. So I want to start off with talking about what is materials design and why we should be thinking about this the way we are. And we had this discussion this morning about 60s and up to 60s. Most of pavement design and material design process was empirical in nature. And then since then, we have slowly moved into performance prediction, more heavily so on using mechanistic methods for performance prediction. And I think the future is where we use these tools, particularly the performance prediction kind of tools, in a reverse gear and do a materials design, meaning that we look at the requirements and then we engineer the material for those requirements. And it's a very broad idea. I'll try to be a little bit more specific about what I mean. So let's look at something empirical too. This is just an example of the penetration test. In fact, many countries around the world still use the pen grade asphalt binder. It's an empirical method. You take a needle and you stab the asphalt binder and see how stiff or soft it is. Maybe it was an improvement over when I was taking a course. My professor told me in class that there was a test called the chew test, where you actually chew the asphalt binder and figure out if it is good enough for the test section. So maybe this was better than the chew test for sure. And particularly depending on whether you not have dental coverage. But so yes, and this is a good idea. It took things forward. But then over time we realized we're engineers. We don't necessarily, we understand better physics and chemistry and mechanics. So why just stab a needle? Why not measure something that engineers can recognize and relate? That would be stiffness, tensile strength, viscosity, and so forth. So we moved into viscosity measurements and things of that nature. This is another example of an empirical test which we use even today, mixture rutting, for example. We're using a Hamburg wheel tracking device. It's at the mixture level, this is an empirical test. You don't have steel wheels on the roads. It's a very harsh condition. We're not really simulating or measuring anything that is fundamental. But it's a good test. It's a go, no-go test that tells you whether or not to expect problems in the field. So it's an empirical test, another example, but so the binders at the mixture length scale. And then we have somewhat of a quasi-empirical test like the overlay tester or the indirect tensile strength test. Now, depending on how you look at these tests, these could be either empirical or they could be very fundamental. If you look at it very carefully, tease out the right measures out of these tests, you can get some more deeper insight. But you could also run these tests as a go, no-go test, pass-fail test, and so forth. There's nothing wrong with simplicity. I mean, I always wonder, every time I travel, I always wonder that there's a pilot who's flying this plane who's got all the avionics, the most sophisticated equipment in front of him or her, and he or she is flying the plane and all of that. But every time you land and take off, there is a windsock on the runway that's blowing that tells you the direction and speed. What does the windsock cost? $100? But it's still there on the airport. It tells you something very quickly and very easily what's the direction and where it's going. So sometimes you need a windsock. Sometimes maybe a penetration or Hamburg. There's nothing wrong with having these kind of a windsock, a quick test that tells you good or bad. But yeah, you can certainly do much better. You can be much more precise, much more robust in what you're doing if you have better avionics, if you have the technology on your side, more the science on your side, the mechanics on your side. So just because I'm talking about a progression does not mean I'm saying that we should totally abandon this or this is wrong or bad in any way. It has its place in the business. This is a picture of George Boggs, who's a professor in structural engineering from circa 1920s. And what he's doing here is that's actually a model of a bridge. It's a section, a model of a bridge frame right there. And what he's doing is actually replicating that model and using a microscope to measure strain. So it's got markers on the model, and what he's doing is applying strain. So he's applying displacement on this and measuring the strain and evaluating whether or not the mechanics is really, or whether the calculations of how much the strain the bridge is going to experience, how much does it fit, or how accurate is it in terms of the mechanics of solving an equation and trying to find the stress strain distribution. Now, if I told you this is how we design bridges today, and the flyover that you're going to take when you go back home, this is how it was designed because somebody in a lab took a little piece and stretched it and figured out that the small lines are not deviating more than 2 degrees, how confident would you be in driving over that bridge? Yeah, so structural engineering has moved away from that. What we do now in structural engineering is we measure material properties. We take a piece, we take a fundamental measure in the lab, and then we solve the geometry. We put that property, we measure something that is independent of the geometry, and then put that property in the geometry to to figure out and predict how it is going to behave. We have an arsenal of tools, a very well developed field of mechanics and structural analysis and design that helps us package all of this information and predict what it is. We're no longer using little toy arches in microscope to predict how the bridge is going to deform or where it's going to fail. That's a progression in structural engineering. I digress with this particular slide here because I want to point out that that is somewhat the same idea where we are in terms of in terms of pavement engineering. We spend a lot of time in empirical methods, and we're slowly taking advantage of mechanics, of computational power, to use these to our advantage for a more mechanistic approach. So structural design, we are familiar with a number of different methods of doing structural analysis of pavements, whether we talked about the mechanistic empirical design guide. And certainly that's an improvement over the structural number, but one can argue that these kind of design guides can also get very sophisticated. Again, another example from, another analogy from the structural engineering field was that, particularly if you look at codes for earthquake engineering, the building design for earthquake engineering does not require you to conduct sophisticated levels of finite element analysis for every single building. But what it does is it takes computational tools, it takes numerical methods to develop codes which are then used by engineers. I think that's a model we also ought to learn from the structural engineering field, is that can we take all of our sophisticated analysis and take all of these tools that we use for pavement design and develop guides, improve our current practice, and move forward from structural number approach to do pavement design. The same ideas can be applied at a smaller length scale on mixture design. So this is from a paper with a number of colleagues of mine looking at moisture damage. You can look at any particular form of distress in the pavement, and you can use a mechanistic approach. In this case, Sylvia, Caro, Ian, Prasad, myself, and Dallas, we worked on this project many years ago. Sylvia is now a faculty at the University of Los Angeles. And this was a mechanistic approach looking at how moisture infiltrates or how it diffuses into the asphalt mixture, and when it diffuses into the asphalt mixture, what is the amount of damage it does, and you can simulate it. Again, if I talk about mechanistic methods, and if I had to do this for every single mixture design, that would be extremely onerous and probably not practical. But I can use these tools to develop guides. I can use these tools to say that under these circumstances you can expect problems, under these circumstances you cannot, and make our guides simple but yet informed and backed up by a sound mechanistic analysis in the back end. Some more performance prediction tools. So this was looking at healing and cracking. How do we combine healing and cracking into measuring fundamental material properties? So this was work that we've done before on developing a test protocol that in a single test protocol you can measure both the fatigue cracking resistance and healing in an asphalt mixture. Professor Richard Kim in North Carolina has done a lot of work on cracking, and this was the same work or same basis that with Richard Shapree's work of damage modeling that is now we use it for healing as well. And it's a single test. You run the test in several different protocols, you analyze the results, you get a material property, and use that material property to predict healing and cracking at different conditions. But again, this is sort of an example of how you're slowly shifting from empirical methods to more mechanistic methods of characterizing materials, of predicting performance. In all of these cases, again, we are predicting performance. We have a structural layer, and we are trying to predict how it's going to perform in terms of rutting, cracking. We have a mixture, we're trying to predict how it's going to perform in terms of moisture damage resistance, how it's going to perform in terms of cracking, how it's going to perform in terms of healing, and so forth. So now we have a fairly sophisticated body of knowledge that has looked into these mechanistic models and associated test methods. So you're always looking at a combination of test and model, because you cannot test every single combination of material that there is out there. So you take tests, fundamental tests, combine them with models, use the two together to predict performance. Materials design would be, now let's take the performance that we want and reverse the knowledge base that we have to turn around and design the material. In other words, if I have a certain number of variables in in my design or a certain number of variables that I can play with or manipulate, how can I optimize, or what is the optimal place in which I can go back and select a mixture design? If you were expecting that I have the answer to that, I'm sorry, let me just tell it right away, I do not. We are still in the forward stage, but I think the expectation when we are working the forward stage, the expectation is that whatever we are doing, we should build towards that goal where we can take all this forward progression knowledge, performance prediction, and at some point turn it around to material design. So the question is, how do we build our knowledge base moving forward so that we can then turn it around and use it for material design? One way to do it is computational tools. So this is in the mixture length scale. What does it mean by material design? Well, what can you change in a mixture? Change the size, change the gradation, you can change the shape and angularity if you have a choice of different aggregates from different sources, which very rarely you do, but if you do, these are the variables that you can change. So, and if I go and look at the design specification, you'll see there's a very large band of, there's an upper limit, lower limit of the gradation, the size is based on the thickness of the layer and so forth. So we use rules of thumb to right now arrive at something. Most of the time it's not even rule of thumb. The contractor usually sees what worked best in the last project and probably just spin off of that, develop a mixed design and then use that mixed design for execution. So if you're looking at performance prediction and looking at material design, what that would mean is that if I had all these variables, what can I find? What is the most optimal combination of these three moving parts that I can piece together to get a product that meets my performance requirement? And one of the things, one of that area, and I know a lot of you are working on that research, so are my colleagues across the world, is to create libraries, is to create computational tools and libraries that have done this in the forward process. So you can take this mix in a virtual environment, compact it, and build a virtual library of this thing and look at the performance. So in this case, this is just a simulation, but in the simulation, the aggregates that we have are real aggregates, or not real aggregates, but they are virtual aggregates, but they are scans, 3D scans of real aggregates. And there's now, we're building a library of these aggregates from different sources and so forth. The beauty of this is that if I have, between my gradation points, I have infinite possible gradations that I can go through. And it's impossible for me to try all these infinite gradations in a lab environment. So what I can do is use a virtual environment to create these samples and test these samples under different conditions. Test them for what's the void content, test them for their stiffness, stability, so forth, and pick the 2 or 3 combinations that are the best and use that for the design. And it doesn't have to be, you don't have to run this simulation every time moving forward. You can create a library of these materials, you can create a library of this forward predicted models, and then turn them around and look at what kinds of properties give you what kinds of performance, because that is something more useful and practical. I cannot expect a DOT engineer to run these simulations for every single mixed design. But we have now computing power that can do this on a scale that is large enough, and we have data accumulation capacity to take all of this information and package it so that it can be turned into useful design guides. I think that's one example of how we can use material design. Let's go to Asphalt binder, which is something that I'm a little bit more involved in. And by the way, I have to tell you this interesting. All of this, or most of this work, was actually started by a student who is a freshman undergraduate. His first class at UT was with me as a freshman undergraduate. He never left. He's not even a civil engineer. He's from petroleum engineering. Super sharp kid, and now he's a graduate student. And it was amazing. He would go in and say, Dr. Bhasin, I figured how we deal with this. There is something called viscoelasticity, and there's something called this equation of this model, and I found it, and I think we can use it. So he was a very energetic, sharp guy. And so, but anyway, we'll go to the binders. So with asphalt binders, there are a lot more moving parts. So this is something that comes out of the refinery. As asphalt binders are refined and produced, manufacturers or producers add additives. They add modifiers. Or rather, let me just rephrase that. Modifiers is the binder, something that the binder producers add. So you can add polymers. You can have, between polymers, you have several different species of polymers. They could be chemical additives. They could be elastomeric polymers, plastomers, and I've worked with a number of binder producers to figure out or to try to understand how they do this, and all the time what they're doing is cost optimization. Really, engineering is about cost optimization at the end of the day. If you can't get the finances part of it right, there's no point in designing it. So what they do when they design these binders is basically they're optimizing cost, and they're trying to see these are the specifications in the book and what is the lowest cost that I can spend to achieve those targets, and they will use a mix of techniques. So those are modifiers. Then you look at additives. Once the bitumen is supplied to a hot mix plant, the hot mix plant may add additives. So they may use a warm mix agent, a compaction aid, a recycling aid, or a combination of all of these things. They may add hydrated lime. So all of these things changing the binder chemistry and composition. Extenders. Recycled engine oil bottoms were very much in fashion a couple of years or 3 years ago. A lot of people were using that and it backfired. There are other waste products, a lot of talk about bio binders. These are extenders. You take the asphalt binder and you change a significant portion of that binder with something else. Sulfur is another extender. You can replace 30% of an asphalt binder safely, more or less, and use that as an extender. So you have extenders, bio binders, and things like that, where you're changing a significant portion of the original binder with something else for different reasons. Maybe it could be environment, maybe it could be cost, and so forth. And then you add wrap, which is really an old binder from an old pavement. So at the end of the day, you take all of these things, and all of these things change the composition of the binder. This may pass the specification at the lab, and it may be shipped to the hot mix producer. The hot mix producer may add any of these things. And what can happen is that every time you're adding one of these, you're altering the composition. And oftentimes, we don't track this change in binder composition all the way as it's happening in time while the mix is being produced and placed in the field. And if composition changes, so does its stability. You can mix several things, and you can stir it up, and it looks good, but after a while, it'll settle down. You can add sugar to water, and if you add too much of it, some little bit of it will be okay. You add too much of it, let it sit. You'll see crystals of sugar. You'll see sugar settle down. Right? Just because you mix two components doesn't mean they're stable. There was a very embarrassing pavement failure in UK many years ago, where they had a binder which they produced by mixing two different binders, and they used it with a porous aggregate. And what happened was the porous aggregate selectively absorbed some of the fractions from the one binder, leaving the rest of the concoction unstable. And that unstable concoction separated, and the road fell apart in a matter of a few months. So it was a really embarrassing situation. But the thing is, you can mix things up, but just because you're able to mix it up doesn't mean that it's stable. Another example, just take that rice and water analogy. If you boil the water, you can add a lot of sugar to it, and it'll tolerate it. But you leave that sugar syrup in your refrigerator, what happens after a few months? It starts crystallizing and breaking down. These things happen in asphalt binder, not to the degree and extent as I'm talking about, but these things do happen, and you've got to be very careful that your system as a whole is stable and it stays together. Microstructure. The stability of the binder influences the composition and stability dictates what the internal structure of the binder is. So binder, we assume it's a homogeneous liquid, but it is not. It's got a structure inside of it. And that structure in turn affects performance. All of these things, composition, stability, microstructure, dictate the stiffness of the binder, its ability to resist adhesion, its ability to resist cracking, healing. All of these ultimately go back to the composition of the binder and how it comes together. So we started taking on this problem and trying to understand. Again, material design would involve that you tell me what are these characteristics that you design, and I will tell you what additives and modifiers wrap and whether the system will work or not. So it's reverse, right? But before you go in reverse, you need to understand the forward mechanism. You got to understand relationships about what things influence the composition in which way. How composition influences stability, how stability influences structure, and how structure influences adhesion, cracking, and healing. And we're still in the forward part. In fact, what I'm about to show you in the next few slides is a jigsaw puzzle that is put together over several different projects by collecting little pieces of information and trying to keep that information contained within a larger framework. I mean, ideally, I wish somebody would write me a multi-million-dollar check and I would just solve this one problem, but that's not how the real world works. So we try to have a bigger problem and we navigate with these smaller studies while we are solving these smaller studies, try to navigate and try to see how we can put this jigsaw puzzle together. Okay, let's start with composition. Since we are in Illinois, I have to quote Abe Lincoln, somewhere you're born. So this is a nice phrase. Give me 6 hours to chop down a tree and I'll spend the first 4 sharpening the axe. So composition you can do many different ways. You can get functional groups from FTIR, you can get molecular size. But one of the most important ways in which you can characterize the composition is what is referred to as the SARA analysis, saturates, aromatics, resins, and asphaltenes. This is based on the polarity distribution. It's important because this polarity distribution gives the material its stiffness, gives the material its strength, gives the material its stability. If you have a distribution of these polarities that are not healthy, what happens when you mix oil and water? You got a very non-polar thing with a very polar thing, you mix it, they separate. So you don't get a system. You add water, soap, and oil, you get something that is a more stable system. So you have to look at the composition, you have to look at this polarity distribution. And as I mentioned, polarity is what defines or what tells you how stiff the overall material is going to be, because it is these forces between these molecules that actually give it its stiffness, and it's the forces between the molecules that give it its strength. And you're trying to balance a chemistry so that your binder is stiff enough on a hot summer day under slow-moving traffic to not deform, and yet it's soft enough in a cold winter night not to crack because of low temperature, or not to become brittle and start cracking because it does not relax stresses. So we did SARA analysis. My first student, she did 4 binders in her entire PhD. And it required a lot of equipment. I remember I haven't learned after so many years working in Asphalt lab, I still have light colored shirts. I don't know why. I should have all dark colored shirts, but I remember going into the lab and one of these columns bursting and the whole solvent and asphalt was over me. So it took her entire PhD to run 4 binders under different combinations and so forth. We tried iatroscan. There's a lot of repeatability issues. It's almost an art. You have to almost like, it's like practicing Tai Chi to have the perfect drop in the perfect time and burn it in the perfect way to get repeatability. So then I approached another research entity, not a university, and said, can you test these 20 binders? We want to do a large scale study. They said they're going to charge me $40,000 for 5 binders. I was very frustrated. So I came down to my grad student and I said, I'm going to give you $500, make a method that we can get this SAT analysis. Doesn't have to be fancy, but it has to be doable, it has to be fast throughput. He spent $5,000, okay, instead of $500, but we came up with a method. So the fast SATA was sort of the first. We spent a lot of time in just making the method simple so that we could do a large volume study. So this is all the equipment you need for the fast SATA. A very nice balance. This is the most expensive piece of equipment. Maybe this is about $5,000. This is the only one that's $5,000, and this is $600 and a vacuum pump. Oh, you need an oven, but most labs already have a vacuum oven. And you can do your SATA analysis using, that stirrer is $70 on Amazon. So you can put this together. We got repeatability that is better than the existing methods, and we could do a large volume of binders. In fact, this method took 3.5 years to develop, but in that one summer, one student was able to run analysis for all these binders, and we could do all kinds of comparative studies and whatnot. This is one undergraduate student, by the way, one summer, instead of 4 binders in 4 years. And this one is just one relationship that shows, how G star over sine delta changes with SATA. But our ability to measure this composition gave us on a large scale, and that is also something I observed in my own research, in my own thinking. Many years ago when I was a graduate student, I would look at 4 data points and try to explain how the universe was formed. And now I look at 400 data points and try to draw just one conclusion, if not, it's more robust. So with this, the idea was, let's do a large, massive study and with as many diverse binders as we can. And that is what we were trying to do here. We now have partnership with 3 or 4 other universities across the world. And this November, late this November, we'll having our first workshop and trying to figure out how do we collect all this data and put it in one unified database. It'll perhaps be one of its kind global database for asphalt binder chemistry with binders from literally all over the world. The second step was stability. So stability is measured in something called Hansen solubility parameters. This maybe due to color contrast, this may not be clear, but you can see here that there is separation here and there's no separation on that extreme. You can do this. Think of it this way, again, oil and water. You can put oil and water, but they'll not be stable, they'll separate. Now, you can take oil, water, and some soap, and you will notice that they're stable. Now, if you try to back down on the quantity of soap, at some point you will see the system becomes unstable. So the stability idea is, what can you dissolve with what? So the way you measure stability is using 3 metrics of stability. You have a dispersive component, a hydrogen component, a nonpolar component. Just think of this as a 3-dimensional scale for measuring dispersion of different fractions, or the solubility of this fraction. So this triangle here tells you the stability of one particular virgin binder. If you remember your chemistry, how many of you love chemistry, by the way? There's only one. I think he's also from Austin, so he had no choice. Very soon he's going to be your colleague, and you'll see him here, so maybe he'll promote chemistry a little bit. That's okay. Nobody raises a hand in my class either. But you all remember like dissolves like, right? That's something chemistry 101. It's the same thing. If you look at the solubility of this virgin binder here and wrap here, these are 2 different systems. And the closer these 2 systems are, the more they're likely to be compatible with each other. So if you look at these 2 systems, this is a wrap binder, this is the original binder. If you're trying to mix them, you can clearly see they're not compatible, which is fine because you can tolerate some degree of incompatibility, but not a whole lot. Here's another wrap binder. So you look at this triangle, and you look at this other triangle. This is on one wrap binder, this is on one wrap binder. Now you can clearly see that the second wrap binder is much more conducive to work with this particular virgin binder than the first wrap binder. Again, we can take this and tease it out further and look at what it means and how compatibility affects performance and so forth. But at this point, I just want to give the high-level idea. There is, take this composition and you impact its stability. There is the person who loves the chemistry there. And then we take this and look at things like cracking, microstructure. So stability, we go to microstructure. This is a very humbling lesson. This is a lesson in sort of humility. A lot of people have done or looked at research on atomic force microscopy. So this was some of the first work came out of a Spanish research group, and then one of my colleagues in Western Research Institute did a lot of the study, where they were looking at the surface of the asphalt binder and they were looking at these structures. So you would use an atomic force microscope, which is like any other microscope, except you don't use light to watch the object. You actually feel the object using a very sharp tip. So think about it. If you're blindfolded and I give you a pen and say, traverse around a path and then draw me what the surface looks like, you'd get some idea of, depending on the friction and how the pen is moving up or down or how it's gliding or rough surface, you can get a picture of what's underneath that pen, even if you're blindfolded. It's the same thing with atomic force microscope. So we started seeing all these structures. Last week I went and did a literature review. Not literature review, I just went to Google Scholar and said, AFM and asphalt binder, like these 2 words, how many papers? There were hundreds. I mean, at some point I said, I can't keep going to next page and next page. There were at least 200 plus papers that I could count in this whole area of studying B structures, what happens when you change the temperature, what happens when you do X versus Y, how B structure, modeling B structures, measuring viscoelasticity of B structures. I must admit, I also have 5 papers in that pool, in all of them. A few years ago, when we were trying to do this, and I was working on a different problem, I was looking at healing and I wanted to measure interfacial diffusion. And I came across a technique that could be used for this interfacial diffusion. It was a second harmonic optical method. And when I read through the technique, I thought, maybe I can replicate this in my lab. And as I started doing a little bit more research, I realized I'm way over my head. So I did the next best thing. What? I just Google search, who knows how to do this? And I found somebody who knows how to do this on our campus. I went to a professor in physics. I had a can of asphalt. I went to him and said, yeah, I'd like to work on, doing this, and this is what I work on. I was positive he's going to throw me out because he started by saying, we work on semiconductors. We're looking at how semiconductors can now be grown and layer by layer on each other. And then there was, I went with this gooey can of asphalt with, sticking. I put it on his table. It left a dot on his table. And then he said, but I'm bored. This looks interesting. After that, we've had at least 2 master's theses and 1 PhD dissertation come out of our collaboration with the professor of physics. And Ramesh Haj here, hopefully soon to be Dr. Haj, if he passes the exam, that is maybe. I'm just teasing. And he's doing great. So he worked very closely with another PhD student in physics to look at some of this stuff. As it turns out, all of this is just an artifact. All of this is an artifact because and this is an interesting experiment that Adam Ram is a student. Adam and Mike Downer, my colleague in physics, did this experiment. We did this experiment by taking the binder sample, exposing it to air, exposing it to a glycerol bath, and exposing it to different interfaces. We were actually, there's a simple formula that can tell you what is the wavelength and what is the size of these structures. And it is everything to do just with the surface tension. That's it. This is purely a surface phenomena that has to do with the interfacial tension between the surface and the air above it. There's nothing more to it. Yes, it is dictated by the composition of the material, but it is not a bulk phenomena. It's not a phenomena that is deeply related to how the binder structure is and so forth. But amazingly, including myself, we got carried away and we did a lot of research. A lot of people did a lot of research. But just last 1 or 2 years, we have been finding out more and more that this is just an artifact of interface. So this formula can actually just predict based on surface tension of the binder and the liquid or the air or vapor that it's exposed to, what these structures are going to look like. So it is, at the end of the day, you're looking at the surface. So when they say don't judge a book by its cover, this is what the story meant by saying, don't look at an AFM picture and try to judge the asphalt binder. There's more to it. And that's where we came in with some other techniques, and Adam and his advisor, Mike Downer, my colleague, we worked on this technique. And so if you look at this cartoon, this is using optical methods. Look at this cartoon. There's surface structure, B structures that everybody knows. And there's structure in the bulk, the green dots. And then if you put anything on top of that surface structure disappears. So that surface structure is an artifact. And what really stays behind is the B structure. And you can see some of this real-time images using optical methods. You can see the surface structure. This is what it looks like. And the B structure in the bulk, if you look at it using dark field microscopy, this is what the B structure looks like. And the idea is very simple. This morning, some of you were in Professor Al-Qadi's class, and Sichi was talking about GPR. I just saw him. Yeah, so he was talking about GPR. So some of you were there this morning, but when you were there this morning, or you've taken the class before, he was talking about GPR. He said, if you change the wavelength, your penetration depth changes. That's exactly what the principle is here. Instead of using several gigahertz, you're using a much higher wavelength. But if you change the wavelength, you look at the surface. If you change it a little bit, you penetrate the surface a little bit deeper. So exactly what he was talking about this morning, Professor Al-Qadi was explaining this morning with the GPR, the same idea, except you're using lasers and at a different wavelength, totally different length scale. It's the same idea. You use shorter wavelengths and longer wavelengths to penetrate, to go shallower or deeper. So microstructure, and then there are studies where we've shown that this microstructure is not just structure, it actually impacts rheology. It changes the stiffness of the binder. So if you measure, for example, if you take a binder, this has implications how you test the binder in the lab. If you take a binder sample and you take it from the oven and you cool it to, let's pick a temperature. Let's say you cool it to 25 degrees Celsius. You take an asphalt binder sample, cool it to 25 degrees Celsius, measure its stiffness. Now you take the same sample and put it in a freezer and warm it up to 25 degrees Celsius and measure its stiffness. you'll get two different things. You'll see very different structure, and you'll see a very different stiffness. For some binders, that difference in stiffness is small, it's 10%. For some binders, it's 25, 30%. So you can see for the same binder, same frequency, same temperature, just depending on whether you are heating the binder or cooling the binder, you can end up at different points. Now, practically, you may say, well, if the temperature changes, the binder stiffness can change by an order of 10, or instead of, so why should we worry about 20%? That's true, but at the same time, it gives you some idea of when you're measuring in the lab, it gives you some idea that these structures are changing and how they play a role in the performance prediction. All of this taking and trying to predict performance. This is a picture from a magazine. East Lansing, Michigan. This was a truck with material to fix potholes. It got stuck in a pothole. Enough said. So it's telling you that the crew trying to get it out. It's not photoshopped, it's a real picture. So adhesion, moisture damage, potholes, things like that. So this was some of the early work related to surface-free energy. And when I was talking about libraries and material design, you can take composition, stability. You can actually measure or predict the surface-free energy of these materials. So here you have surface-free energy for all the binders. You have surface-free energy of all the aggregates. And the idea again was to develop libraries for purposes of material design. And this is what such a library would look like. Once you have these measurements, you don't have to test every single combination. You have about 10, 15 binders here, 10 different aggregates. So you have like 150 combinations. But if you measure the binders and aggregates, you can use mathematical modeling to predict the outcome. So in this case, you can see that some of these binders, if for any given binder, different aggregates and different responses. This one, the red color would mean you can expect moisture damage. This would mean it's going to be good. So one aggregate works very well with this binder. Another aggregate does not do very well with this binder. And then the other way around, you can take an aggregate and you can see all of these binders. Some of them do very well with the binders, some don't. So you can make these kind of decisions by using such a table or library of information. Cracking, Ramesh Haj is here. This is work he was doing with Adam. And he's going to answer all the questions after this as well. And that's why he joined me in this trip. So this is the work. This is actually now going a layer deeper and understanding why are these cracks formed? What is the role of structure, microstructure in forming these cracks? For a very long time, the hypothesis was that if you have a structure, if you have a discontinuity in a material, that acts as a seed for the crack to grow. And we then hypothesized and discussed for a very long time that perhaps if we can manipulate through thermal conditioning or chemical changes these structures, we can stop the cracks from nucleating, and if we stop the cracks from nucleating, we can perhaps stop the cracks from, or extend the fatigue life of the material. So that was a hypothesis we started off with, and we started exploring this cohesion test with the microscopy involved. So there was a microscope attached to this cohesion tester that we built to watch the cracks form. So this was what Ramesh is working on. As you can see all of these microstructures in here, and as you apply a cohesion test, this crack nucleates from this one point in the form of what is now we refer to these as cavitations or cavitation, and that crack slowly nucleates and grows in size. But the other thing that you observe is that this nucleation does not happen at every single point where there's a microstructure. Just randomly, some of these microstructures participate in crack nucleation and some of them don't. This, by the way, it takes a very long time to capture a picture like this because it's a trial and error. You may be looking with microscope over here, the crack may be forming over there, so you don't know, so you have to run on multiple tests before you can actually capture one of these images. Ramesh is very well familiar with the frustrations of doing this and frustrations of me sending him back to the lab every time. But eventually he did it. He caught these things, and then he repeated the same thing with fatigue. So this was a fatigue phenomenon. If you look at that crack, you will see how the crack nucleates and grows. You can see that crack is now growing into these micro cracks and spreading and connecting with other things. This is very insightful because I can tell for the last 20 years or so, every time I've been talking about cracking, I've drawn these cartoons of a little micro crack that is growing over time. This is actually for the first time visibly able to, or visually able to see these cracks nucleate and grow into these micro cracks, then coalesce with other micro cracks to form macro cracks. You can see how this forms and grows. This is all in a microscopic length scale. By the way, the other thing that you notice here is this white cloud that is moving here. So this is at a much lower length scale, so you can see a large area. This is of the order of a couple of millimeters now. So these white clouds that you see here, these are the microstructures. So what happens is, very few of these microstructures trigger the crack. The rest of the microstructures are simply inert. Once the crack starts, the other microstructures don't initiate cracks, and they simply float around, or they get pushed around over this. We take these ideas and we can develop this into, again, this is forward thinking. This is our jigsaw puzzle where we are connecting composition to stability to microstructure and planning. Again, keep in mind in this forward process, there are two things. There is testing, measurement, and there's modeling. And every step that I've tried to express here, the composition to stability and microstructures, we have models that we are trying out. And where we are in the grand scheme of things, we are here, composition, moving on to stability at the moment. There is a pilot, or there is proof of concept all the way down up to here, but really for us to draw larger conclusions, we cannot do 2 binders, 3 binders, and then draw large conclusions. So our goal is to have hundreds of binders, run through the schematic, and create a large library so that that library can inform us in a more reliable way what to expect when you do X, Y, or Z. So that library that we are working on right now has several different binders just from within the United States. I'm hoping that in our partnership with other parts of the world and within the United States, we continue to grow that library. Maybe we spend 2-3 years on this, but when we are done, we come up with 3 or 4 solid conclusions of exactly what to do and what not to do. And not only that, when you have newer additives, newer modifiers come into the market, we can also predict what's going to happen or try to use these tools for that. This same picture just to demonstrate healing, so you can see that crack after setting aside or leaving it letting it sit for, I think this was several hours. You can see that crack, that micro crack is actually healed, but you would see that that healed portion has no microstructure anymore. The microstructures have all been pushed into this area here. So this is post-crack healing, which is technically healed. The crack is closed, but it's now different bitumen here as it was over there. So this will always remain at the very minimum a different spot or a different location from a healing point of view. So what is materials design? So to recap, where we are right now in developing all of these tools is just we're building little pieces of this puzzle. We haven't solved the puzzle, and it's a good thing because that way I can keep my job. If we solve it, then I have to go look for a new problem. So we're looking at these little pieces of puzzle, and each one of these boxes is a little piece of puzzle that needs to first come together in the forward direction, and it has to come together in the forward direction at a very large scale. We cannot draw conclusions based on 3-4 binders. It has to be done with a very large diversity of binders, diversity of asphalt binder chemistries, rejuvenators, wraps, warm mix agents, all of those things. And once we're done with the forward process, the idea is that we reverse this, and then based on the expected performance, we can say which modifiers and which additives and extenders are best compatible with which other, what other binders and so forth. Because it's very similar to the chart that I showed you with the surface free energy, the adhesion. Some binders and some aggregates work together for adhesion. The same idea is that some additives and some binder chemistries and certain kinds of wraps will work together very well, while others will not. We in fact just finished one study where we showed how some of these combinations can be counteracting in each other. In one case, it was a very high quality binder with a lot of SBS polymer, and one of the additives simply dissolved that polymer and destroyed it. It's something that would never be captured in the specifications. Now, before I wrap this up, I also want to emphasize that thinking in this direction, materials design, whether it's asphalt binder or asphalt mixture, or even a pavement structure, the same ideas can be extended to other length scales, binder, mixture, structure. When we're thinking about these problems, we cannot think of these as simply experimentalists. We cannot simply think of this as modelers. I'm guilty of crimes over here where I've done testing and just drawn empirical conclusions. I'm guilty of crimes here where I have done modeling by simply pulling numbers from thin air or looking at some past papers and saying, well, XYZ used 0.4 to 0.5, so I'm just going to use 0.45 and do this model. I've done that, and I'm guilty of that. And I've done experimental work. We're looking at engineering mechanics, we're looking at science, but I think the right way to solve the problem is when you combine these two, is when you understand that modeling must be informed by real measurements, and real measurements must lead you to a model. You cannot simply make real measurements for the sake of making measurements. They must have some fundamental material property that can be wrapped into a model. If they don't feed into a mathematical framework, into a physical framework or a chemical framework, then you're just making the measurement for the sake of making the measurement, and that's not a good use of time. These two have to feed into each other, and so do these two. You cannot decouple mechanics from physics and chemistry and material science, and so you have to put these axes. And so we're talking about scientists versus engineers, or experimentalists versus modelers. You got to understand that solutions are at the intersection of all these fields and not in any one side of it. Some collateral benefits along the way. I just also want to point out, like I said earlier, this is just 2 or 3 more slides. I don't know how we're doing on time, but these are just 2 or 3 more slides. And just to show that this looks a lot of pie in the sky, modeling and framework and building an asphalt binder genome library and so forth. It looks like an ambitious out there idea, and there's nothing wrong with that. I think we should all try it, because if we haven't tried it, how do we know it works? But at the same time, I also want to point out that we're engineers. When I interviewed at UT Austin, a couple of my colleagues from transportation, they looked at my research papers and asked me this and said, are you going to do this? I was working on surface free energy, and said, are you going to be working on this science, chemistry, physics stuff, or are you going to be doing more the engineering stuff so that we can get research dollars from the DOT and city and county? And my answer to them was, I'll do a little bit of both. And I also followed up my answer by saying that I'm saying I'll do a little bit of both, not because it's a diplomatic or a politically safe answer because I'm checking both boxes, because as an engineer, my primary job is to solve problems, to make practice better. But also, and if I were a scientist, I would just do things just for satisfying my curiosity. But also I realize that within the realm of science, there are so many developments and so many tools that are coming up that it behooves me to step into that territory and pick up some of those tools and understand that and bridge the gap and bring them into practice. So at the end of the day, we have to solve practical problems. So behind all of this map of doing materials design and binders or mixtures, there's also some practical advantages. This, for example, is a cohesion test. Ramesh was involved in some of this study. In fact, it forms part of his dissertation. And if you look at asphalt binder specification, a typical specification, these 4 binders are the same specification. These 4 binders are the same specification. And part of our study or research about fracture and looking at microstructure, in that process, we also developed this cohesion test, which we refer to as a poker chip test. It's not the name we came up with. It's a test that was developed in the 1960s in aerospace and engineering mechanics to look at adhesives. And when we developed this test as a part of what we were doing in the previous, what I've shown in the previous slides, we could see certain things. Like, for example, these 4 binders are all PG64-22, but look at their tensile strength. These 2 binders under the current specification are rated to be exactly the same or very similar, but look at their tensile strength. Am I not to deduce that their fatigue lines are also going to be different in this case? Look at these 70-22 binders. Look at these 2 binders. Look at their tensile strengths. Am I not to infer that these 2 binders that are considered to be equivalent replacements of each other will have the same performance? So we took this information to the DOT and they started looking into it and using it, and we're now working on an implementation study and using a cohesion test on a routine basis. So this is part of one of the Ramez's colleague Angelo is working on part of his study. He's looking at several different mixtures with RAP and RAS. And this is an asphalt mixture here, overlay test, fraction energy from that, and this is a fraction energy from a poker chip test. And it's a pretty good test to pick up on what's happening in an asphalt mixture, particularly considering that these dots contain mixtures with different aggregates, mixtures with different gradations, mixtures with different binder contents. So as a practical tool, if I want to test the quality of a binder, the fracture resistance of a binder, this is a good practical tool to do that. Not only that, these also include some mixtures with RAP, some mixtures with RAP and RAS gradation. So you can see how this is a nice screening tool to see what happens with the full mixture. So this is by far not something very fundamental, but something very practical that can be brought into practice in a near short term. The SATA analysis, the fast SATA that we talked about, a couple of cases like this. So this was a pavement section. It failed in 2 months. And one of the engineers involved in this project actually just pulled a chunk off this and brought in a Ziploc back to the lab and said, well, we looked at the binder and everything passed the spec. We looked at the mixture, everything passed the spec. The tap coat, everything, the forensic analysis done, everything passed the specification. So what's wrong? Did the fast SATA, this is the typical range of numbers you would expect. This is where that particular asphalt binder was. It was something that was not detected in your regular specifications, but was detected as a part of this forensic analysis. This was a tool developed out of those ideas. Another example with, again, SATA analysis was this, what looks like a binder, which was really gooey, gunky stuff that was in one of the hot mix plants. And it turns out it was not really a binder, it was some other stuff stuck in the binder, but was going into the same pipeline as the asphalt binder. Again, a very quick chemical analysis revealed that this is just an asphaltene skid got stuck in the pipeline that were creating this problem, and so it's just needed to clean the unit. So again, we've used this tool while we're using this tool to better understand the fundamental relationships between the chemical composition, microstructure, performance, and so forth, and look at a grander, bigger picture. We are also using these tools in the immediate term to forensic analysis and to help improve practice as we are working today. So I'll conclude by this phrase. This is attributed to Ludwig Boltzmann, is that as long as alchemists thought about philosopher's stone and art of making gold, all their efforts were fruitless. It's only when people restricted themselves to very basic questions that they created chemistry. So in the grand scheme of things, we are trying to answer little questions. What happens with chemistry to solubility? What happens with solubility to structure? And in that process, we are also helping the current practice, but we're also creating a bigger picture. Boltzmann, by the way, is a very inspirational figure, except for the part we committed suicide. So focus on fundamentals, mechanisms, models, design, and look beneath the surface. The AFM is a humbling example where there are hundreds of studies, but it's all a surface tension effect. That picture, I love to show that picture there. Now here's a quiz. One of those pictures is from the Hubble telescope. The second one is from Ramesses telescope. One of those looks into the galaxies far, far away. The other looks into the structures deep inside an asphalt binder. Okay, how many of you think the asphalt binder is, how many of you think that this is the asphalt binder? How many of you vote for this as the asphalt binder? Honestly, I don't remember the answer. I have to go back and look at the image files where I found it. Yes, the people behind the research, you will recognize him from sitting here. Alex has worked as an undergrad with me, Saida, Sati, Anand, Angelo, Sakib, Tyler. This is the lab, this is the microscope, the space Hubble equivalent is here, right here. It's a very small footprint device, literally a few $100s. By the way, I was making this presentation someplace, I realized I did not have a picture, so I asked one of these persons to send me a group picture, and they sent me a mug shot as if they were standing in line. So, need to improve their picture taking skills. By law, I'm required to acknowledge my sponsors, but also out of my heart, I would like to acknowledge them. A lot of this work is funded through NSF, DOT, US DOT, Ergon, Asphalt, and so forth. Thank you very much once again for giving me this opportunity. I hope you haven't fallen asleep for 2 minutes of the time.
Any question, guys?
wonderful presentation. So when you're trying to link the performance, here you mean the performance parameters coming out from binder characterization, or at the mixture level you're doing
At the moment, this I think is an ambitious thing to link chemistry to solubility to structure. At the moment, I think it would be a good goal to figure out the performance of the binder. Mixture would mean you're now jumping lengths, and that always has challenges in and of itself. It is an ambitious thing to do, and it could be done, perhaps, yes. It's certainly doable. There's no reason why you should stop there.
Are you looking for something like, since you have the binders tested and all those binders are going somewhere, maybe?
Maybe in a few years from now. It's possible, but it is not something I'm too much. It's not something that I'm too focused on at the moment. But eventually, yes. Primarily also because I've run out of space to do mixture tests in my lab.
Okay. I have a follow-up question. Just so for the binders when you were testing, these are like straight binders, or they are modified binders also? Like
They're all kinds of binders, including binders that have been. Some of these have been run with binders that have wrapped, extracted, wrapped, dissolved. Yes.
Thank you for the presentation. I was just curious for the cavitation, although it was random with the, as you said, the difficulty of finding the right picture to witness it. Have you learned from experimental and or numerical modeling what are the critical conditions that induces those cavitation?
That will be soon to be Dr. Haj's first research project. I asked him to look into that, but he wanted to graduate for whatever reason.
We have some ideas.
Yeah, we have some ideas.
Yeah.
That is work in progress.
Yeah.
Yes.
Because then you don't
Some
have to
part-
hopefully it shows here.
Yeah. Some parts of this, there was modeling done on some parts of this, and then if I go back to the original, if you need to kick me out of here, kick me out if you don't mind.
No, just moderating the question.
If I look at this picture, there are sophisticated models that will take us. For example, there are models that we developed with very high degree of confidence that predict microstructure. But as it turns out, we were modeling the surface microstructure. So we did the modeling, and now we have to scrap it. It's okay. We learned that this is not the right thing to do. But we now know how to model. So we have models that take us from here to here, here to here. This is still work in progress. Even this, I wouldn't say that this is done, but we at least have a starting point. We've done models. There are models that will connect us here, where we need to scale and validate those models. There are models that will take us from here to here. We need to validate those models. This one we even validated for surface, but then, as I myself told you, that surface is not all that important. So even though we had a validated model, it was not useful. At least we think it's not.
And
Yeah.
oh no, sorry.
Go ahead.
I was just gonna say, and on that subject, that's a really good question. I think that is part of what I was trying to solve, but it was a little ambitious for one PhD. So if I do a second, then I'll do it. No, but I think the biggest challenge there is actually we don't even know necessarily 100% what we're looking at yet. So we developed a model in that framework, but it's kind of just parametric with, hey, if the inclusion is stiffer than the matrix, this is what will happen.
Correct.
If the matrix is stiffer than the inclusion, this is what will happen. So that's kind of what we presented there, but we would actually need a stiffness measurement of those components. So I think that's something we're working on too, is once we fractionate those components, or if we have tools that can work at the nanoscale, I think that might be what gets us there to understanding why it's choosing that exact point to form damage. So that's kind of what we were thinking at the moment. Yeah. Hopefully you'll see it in the next few years. So.
Yes.
Hi, thanks for the presentation, very good and very nice images. I have a question about the modeling and the images of the microstructure. Those images were only with binder, right? Only binder. What challenges are to try to incorporate some kind of imperfection, like small aggregates to that kind of specimen that you have, to try to observe the interaction of this imperfection, like fine aggregate, mineral filler, with this cracking? If it's not possible with the equipment that you have, or needs some kind of extra advanced equipment for those images? That would be the question.
Do you want me to take that one away?
Yeah.
Yeah, so the biggest challenge in the dark field technique is different things scatter different amounts of light. So once you start putting in polymer, for example, scatters really beautifully there. So polymer modified is definitely doable. But not sure about aggregates once we start putting like filler size aggregates in. Some types of rock will scatter differently from other types. So it can get very hard to compare what we're seeing in the microstructure. So it's definitely easiest with just binder because those same absorption holds true. But yeah, it's when you start putting in aggregates that somebody actually contacted us and wanted to look at a cementitious material in there, and he just handed me a specimen and was like, can you take it over and see what happens? I took it over and that thing was just like, I don't know, it was like scattering way too much even when I lowered the exposure a ton, lowered the gains a ton, it was just scattering way too much. So I think that would be a huge issue with the fillers, whereas especially comparing between different ones, different types of rock. So it's something we'll definitely are looking at in the future, but it's gonna take a little bit of time.
Absolutely.
Yeah.
Thank you.
Any other question?
Any other questions for Robbins?
Thank you so much.
Right, thank you.
You have the numbers?
Very good.
Okay, let's put them in.
Got a few more.
Yeah, no, I'm actually doing a house hunting trip, but I figured I'd time these trips together so I could attend I'm in seminar as well. So yeah, kind of brought everything together.
Well, yeah, you could
Here.
work on along the way also.
Yeah, I finished half of it on my way here. And I'm like,
There you go.
on the way back, so I think
Is
he's
he gonna stay around?
No, I think he's not traveling with me. I'm not for sure. When you say,
Mr. Allen?
Yeah.
you're leaving tonight?
5, 6.